Thank you, Andre. Good morning, everybody, and thank you very much for the opportunity to come here. I'm absolutely delighted, and you'll see why in a couple of slides' time. Unfortunately, it's going to be all in English. Professor Van Hulk and Dr. Wouter Woedes tried to teach me some Dutch. Admittedly, there was some beer involved. I remembered 3 words, and the 3rd word I'm not allowed to use in public. So, safer we stay in English. Okay, so just a very quick quote there. Wouter had a slide a while ago that showed the book by Dick Steffi, who did an awful lot of reconstructions in America. And that comment there in the middle, I think, is quite relevant. The ships that we find, a lot of the shipwrecks, they're full of all sorts of artifacts, lovely cargo, sometimes gold coins. But for most of us here, it's actually the ship itself is the most important thing. That ship took so much time and effort to build, so many people involved, and without the ship it can't transport the cargo. So it's the ship itself is what most of us are most interested in. As Andre mentioned, I had a bit of a midlife crisis 15, 20 years ago and started becoming involved in maritime archaeology, signed up for a PhD in Southampton. And they got very excited because now they had a boat builder dragged into the world of academic research. And what they asked me to do for my PhD was to look at all of the reconstructions that have been published, all the past work, and do a sort of a review of what had been done. How good, how valid were the reconstructions. I could see straight away what they were interested in was my experience of boat building and sailing and looking at what had been done. So I started thinking about the idea, how could we validate some of the research, because I understood very little Dutch, but I did get the reconstructie interpretatie. Every reconstruction that we do is an interpretation. We never find a full shipwreck, very, very rarely. So we're interpreting and trying to understand what was there and make a hypothetical reconstruction. And it's quite important then that because I've seen some reconstructions, and the boat has to float. It has to function as a ship. That's its primary function. So how can we analyze and test that? Part of my research, I went right back to the beginning, and that's why I'm delighted to be here today. Reuvens and Glaviman, pretty much the very beginnings of maritime archaeology as a discipline. And I love that model that they made. They made 2 models. The first had no interpretation, just a model of what they found. So it's honest, it's true, that's what they found there. And then their second model was their interpretation. Because quite often with publications, you can't go back to the original data, the original information, and question and analyze what has been done in the reconstructions. Some other examples, Nigel Mose from 1865. A lot of the stuff being done at this period was sketches and artist impressions of what they thought that the boats looked like. Another very good example, the Oseberg ship. It was discovered in 1903, excavated and put back on display in a museum. People then subsequently took measurements from that museum display and built a 1:1, what Wouter called a research model. They built a full-size replica of the ship, and on its very first voyage it sank, sailed itself under the bow wave. The reason why they put the ship back together in the museum with slightly wrong angles on the bow and stern, which had squashed in, tightened the front of the ship. The minute they built the full-size replica the same as what was on display, the thing sank. Again, another quote from Dick Steffi. Anytime that Steffi worked on a research project, he built models, lots of models. Even models of little parts of the ship just to try and understand how the whole thing goes back together. For the Carina and the Asiata ships, he built over 18 research models before he finally arrived at a stage where he was confident to put the ship on display in the museum. So as part of my PhD, I looked at all of the different, well, not all, but the majority of the different ships that had been excavated, published, and reconstructed. And I tried to understand how were people doing this process? How were they creating their hypothetical models, and what were they using to analyze and to say, yes, I've made the correct reconstruction. And quite often it's things like coefficients of form, or how much tonnage the boat can carry. We find documentary evidence somewhere that a cog carried 80 lasts. We don't even know exactly how big a last is because it had different measurements in different harbours, not to mention in different countries. We find dimensions written on drawings, 15 feet, 100 feet. Is it an Amsterdam foot? Is it a Swedish foot? Or is it an Irishman's foot? So we've got these inconsistent things that we're trying to work with. So again, I go back to this idea of, can the ship float? Does it function as a boat? After that, then we can start to ask more questions of the ship. So basically, my whole research was this idea of using the 3D digital technology that we have available now, things like photogrammetry, laser scanning, recording the ship as a three-dimensional object, reconstruct it in 3 dimensions, and test it in 3 dimensions. This idea of 2-dimensional paper drawings, you're creating this super complex shape, 3-dimensional shape, you're flattening it into a 2D drawing, and then you're making another 2D drawing. Very, very rarely do these two-dimensional drawings match up. If you put them all back together, you don't get back into a ship again. And you'll see that in the slide time. So part of the research I did during the PhD was to actually test the method that I was using. Document a boat. I was lucky that this actual boat I built myself as well, and I sailed on it. I know exactly how it performs. So we made a 3-dimensional laser scan of the ship. I'll call it ship for the rest of the day. It's only 9 meters long. It's not really a ship, but for us Irishmen, it's a ship. So we recorded the ship using the 3D technology with laser scanning. We were able to get it very accurately measured and documented. It's all within 2 or 3 millimeters accuracy. You also have the benefit of recording the entire boatyard while you're there as well. And we were able to see from the boat, from the digital information as well as the physical information, where the boat actually sits in the water. We know how the boat sits there. And when we know how a boat sits in the water and we know its shape, the only other thing that can change there is the weight. So using Orca, it's a naval architecture software. It's primarily for designing boats for naval architects, but I turned it on its head and said, I have the design, I have my research model, I want to test it with the naval architecture software. It will tell us exactly, can the ship float or not? So using the marked measurements from the boat that we had built, we know exactly the weight, the size, the dimensions of the boat. We have the mark where the water sits on the boat. We're able to put the computer model from the laser scan back exactly as it floats in the real world. The naval architecture software can give us all the calculations and numbers, what it weighs, how much it displaces, exactly how it's, the results, all the information of the measurements based on how it's sitting there in the water. Then I built a digital model of the same boat. So I rebuilt the ship again in the computer. Every single timber, make each one as a solid object and tell the computer what the material is. This is the oak for the beams, the iron for the nails, the canvas for the sails. And we add in all the materials. The computer then tells us what the digital model weighs. Just the timber on its own there in the top left-hand corner. Only timber, nothing else. That's how the boat would float, according to the computer. On the bottom, if we start adding in things like the anchors, the life raft, all the extra bits of equipment that are actually in the boat, we get much closer to how the boat would sit. This is the computer adjusting for the weight of all the objects in the boat and floating the digital model. And finally, with the internal ballast added, so a complete digital replica of the physical boat, and the digital model here on the bottom is floating exactly the same as the actual real boat. The results were 22 kilograms lighter than a 1,400 kilogram boat, so it's 99.9 something% accurate. So I'm happy that the digital approach gives us the same result as what we're seeing in the physical world. After I finished my PhD, I was visiting the Bremer cog. I'm sure there isn't a person in the room who doesn't know the Bremer cog. And a random question was asked at the time. There was a lot of debate. It was back in 2020, maybe just before COVID. So there's historical documents, there's written records that the Hanseatic League trade with Iceland. So they have the Hanseatic cog, and some people started jumping to the conclusion that the Bremer cog is the sea-going ship of the Hanseatic League and it sailed to Iceland. I said, no, I don't think so. In fact, I said, definitely no. So they asked me, could I prove it? Can I test and analyse how the ship would perform? I'm not sure if I could prove it, but as a boat builder and sailor, I wouldn't take this boat up to Iceland. So they gave me all of the data that they had. We had the original two-dimensional paper drawings published by Werner Laat, and we also had a series of digital data captures, either photogrammetry or laser scanning over a set period of time. The first thing that gave us was a very interesting look at how the boat was behaving and changing in the museum during that 30-year period. From the time the ship went on display in the museum, and as it shrunk and dried out and changed shape and deformed, so we get this nice snapshot of a 30-year period of time where the ship is actually changing shape, shrinking and drying out and modifying itself. So that first question was, why is the ship moving so much? So I was able to build a digital model of the ship, and as we know, ships are happier in water. They're definitely not happy in museums. So something the size of that Bremen cog floating on the water, every square centimetre of the surface area is being supported by the water. It's being cuddled and caressed by the water. So with being able to calculate the surface area, we know that on one single square centimetre, there's only 0.06 kilograms of force. It's sitting almost on like a feather bed. If we go and look at what's inside in the museum, because it's only sitting on the keel blocks and half a dozen steel supports, we have 5 to 10 times more pressure per square centimetre on the contact points of the ship in the museum. We're asking a ship that's almost now 1,000 years old to do 5 times more work than we asked it to do when it was built and launched and put afloat. So it's clearly not going to be happy there for any point of time longer. And the other part is, and we talked about it a lot yesterday in the workshop, in order to get the best possible results from the analysis, we need a very accurate digital model. We try to get it as accurate as possible, like we model down to the level of nails and even coatings and paint on the surface of the timber. So I needed to build an accurate digital model of what the Bremen cog looked like. So again, I went back to the original source data. Do you remember I mentioned that paper drawings don't make a ship? We take all of the pointer doesn't work. All of the paper drawings published by Werner Laat, I put them all into their correct orientation, the body plans, the cross sections, and on the right is the shape of the ship if you join all the dots together. So clearly there's interpretations in the drawings. I don't know which ones he used to exactly create his ideal one, but clearly he's used some and not used others, or we get this very distorted shape of the hull. So we have to go back and try to understand which ones try and smooth out the differences. On the bottom was a simple drafting error in one of the drawings. That blue streak is the computer version of the paper drawing with the timber running along the side of the hull. And you can see it comes along and clearly jumps up. He skipped a dot in his counting of drawing in the lines. Small, simple little errors, but they all add up. There were some other things that definitely raised a few eyebrows when I looked at them. Things like this reverse curvature in the deck. We don't see a feature like that until over 400 or 500 years later with modern sailing yachts. Definitely wouldn't want it to be happening in a timber boat where the water would be pooling on the deck and leaking down through it. The cross beam supporting the deck, you can see it's completely missed the bolt hole that's in the stern post, so there's something strange happened there. And there was always this kind of funny discussion argument about the whole windlass in the back is tilted off to 2.5 degrees, which is then causing the deck to tilt off to 2.5 degrees, and is also causing the whole stern castle to be angled backwards. A lot of the arguments, Lan actually published pages about this. It clearly was stuck in his head for some reason. he was arguing the reason why this whole stern castle was at an angle. I don't think it was. I think he just misinterpreted the information that was excavated. One simple straightening of one beam would pull back together all of the crazy funny angles that were happening inside the ship. And when you start looking much closer, you see on the right hand side there, because of that angled stern castle, all the connections and joints between the woodwork beams were becoming opened because of the angle. If we pull the whole thing back straight, it closes up all the joints, makes a nice tight. I don't think they were planning to build loose, not well fitted timber beams in the ship. So again, it's this idea of interpreting the shipwreck. We're working with something that's been deformed over hundreds of years, and we've got to give it a little love and understanding to try and get it back into shape. So I said to the guys at the museum, I want to do I want to reconstruct the Bremen cog. Give it the Irish version of the Hanseatic cog. So I straightened up some of the beams, closed up some of the woodworking joints, mirrored over some of the parts that were missing, and I arrived to a much straighter, squarer stern castle, which I think is probably a more realistic version of what might have been there. It straightened up the anchor and the windlass in the center of the ship. It solved some of the problems of bolts and beams not meeting in the right places. And we arrived at something that looks a little bit more respectable or less twisted and tortured than what was in the original drawings. There is some interesting discussion surrounding that Bremen cog. Some people think it never actually went to sea. It was being constructed and something happened. There was some disastrous event, and they never actually completed the Bremen cog. So the ship, as it sits there, empty, with no rigging, just the timber, the nails, the fastenings, it will float. It's got a little bit of a stability curve there. It's not an ideal stability curve, but it will float. It can be put in the water and moved to somewhere else for further working. Stability curves, for those people, just very quickly, that's what a stability curve should look like. Going up in a nice smooth curve, getting to your GZ max, at your maximum safety where the boat will always come back upright. Once you go beyond that GZ max, you can still sail a little bit, but you need to start being careful. If you go a little bit further, it's going to capsize, which we found out last year with the Carina replica. So the Bremen cog, as it sat there, we knew the weight exactly of all the timber, all the fastenings, all the nails. We started adding in things like the mast, the rigging and the sails, and we can calculate very, very accurately the weight of the ship as it sits. The problem with that is the empty ship without the rigging will float just about. Once we start adding in the weight of the mast, the sails and all the rigging, the ship becomes completely unstable. With no ballast inside the ship, it doesn't have a stability curve. It's got a reverse stability curve. This thing is going to heel over. It might not capsize. It will go to a heel angle until it finds equilibrium, but if you sneeze, there's a chance that it might capsize. So possibly there's my version of a potential reason why the ship might have capsized during its building process. You definitely could not add the mast, the rigging and the sails without first putting stone ballast or some sort of weight into the ship. Again, all this testing and digital analysis, we're able to analyze the results. So that empty ship there with no ballast in it, even if you did manage to keep it sort of upright, and it would be crew running from side to side to stop it capsizing, it fails every single criteria for stability. Nobody would put any cargo or people on board. Definitely wouldn't get any modern day insurance to go sailing on it. So that tells us straight away that the ship needed some sort of ballast to make it stable. During the original replicas and the original modelling of the various versions of the ship, they did some research in the university in Kiel, I believe, and they came up with figures of like 20 ton of stone and all sorts of strange numbers that maybe this is what's needed in the ship. The beauty with the naval architecture software is I can start gradually adding one single stone or one centimetre of stone in the bottom and test the program. see is it stable? No, it's still capsized. Add another 10 centimeters, so I can incrementally start adding until we get to somewhere that the ship will just about function. And basically that's what we do, just keep adding, retesting, adding and retesting. We can also analyse the effect of the wind blowing on the side of the ship, how much the ship will heel over with the wind, with the different amounts of cargo, and basically keep running different tests until we find a set of numbers that say, yes, this can function as a ship. So we're able to tell in low, medium, strong winds, full sail, reef down sail, or no sail at all, what way the ship is able to perform. One of the other things that always interested me is the true hull beams. All of the replicas that go sailing, they all sail with those true hull beams above the water. But on nearly every cog that's found, they have these, what have been called quite often fender blocks, supposedly to protect the end of the beams when it's rubbing up against the stone pier. Strangely, all of those fender blocks are very well carved and shaped, teardrop shaped, pointed towards the ends. If you're only making a fender block that's protecting the end of your beam, all you need is a block of timber there, because it's sacrificial. But if you're making it all aerodynamic, hydrodynamic, teardrop shaped, my belief is that they were fairing the water running around the beams. If you set the Bremen cog with the true hull beams at or just above the water level, it carries a bit of cargo, but not an awful lot. It carries about 40 tons. If you submerge the beams, the ship becomes an awful lot more stable and can carry nearly 3 times as much cargo. Everyone is saying that crazy Irishman wants to sink the Bremen cog, putting the true hull beams under the water. But if we look at the way they're made, there's an awful lot of work in them. They've carved rebates all around the beams, they've put caulking and moss, and there's an awful lot of work in trying to make those true hull beams watertight. And these fairing blocks that are put on either side of them, I'm quite happy with the idea that they probably were submerged. There's some examples there from the dual cog. So again, looking at the performance, it was completely empty here on the left. Zero cargo, the ship does function. It's got a bit of a stability curve. And you'll notice the more weights we put into the ship, the nicer the stability curve becomes. With the beam ends just sitting at the water level, the ship will carry 43 tons of cargo. Now there is a medieval law, it's from the 1200s I believe, the Gragas Codex, it's an Icelandic law for loading sailing ships. And it says the freeboard left from the water to the top of the deck should be 2/5 of the overall depth of the ship. If we apply that law to the Bremen cog, the cargo capacity jumps up to 108 tons from the 40 that will only carry with the beams above the water. And the stability curve becomes an awful lot better. The ship becomes more stable and surprisingly faster. We're also able to calculate the speed potential of the hull based on the shape under the water. And the deeper it sits in the water, the better the boat performs. There's some, we're getting into very dangerous territory here. There's mentions, lots of mentions of ocean-going cogs. There's historical records of cogs of nearly 200 or 300 last. Again, I don't know what size a last is, but we're estimating that the Bremer cog is somewhere around 60, maybe 80 last. So an ocean-going cog of 200 to 300 last, how big is it? And Wooter is very proud of his Eisel cog, which is 2.5 times bigger, I believe, is it, than Bremer? If there is such a thing as this 150 or 200 last cog, that's a comparison of it between Bremen on the left and this so-called ocean-going cog of 150 or 200 last on the right. Well, maybe they exist, but that's a bloody big sail area to be dealing with. And just finally, some of the things that we can do because we make digital models. So here's an example. We put the Bremen cog into the Unity software. It's using real-world physics. So it's actually making the ship float in a real sea condition. We're able to model up what the various, this was the testing, can the ship go to Iceland? So in the Baltic Sea with 1.5 to 2 meter waves, the ship is lovely, it's great fun. It makes everybody seasick, but it doesn't sink. out in the North Atlantic with 15 to 20 meter waves, it does not work. It sinks very, very quickly. And we can do sort of education and outreach things like augmented reality and VR headsets where you have the Bremen cog floating in the room in front of you. And that's it. Thank you very much.
Thank you very much, Pat, for this clear presentation. I'm sure there are some questions, and we have a lot of time for questions, so...
Very well.
There is one fascinating thing, and that's the rig.
Mm-hmm.
The rig here is taken as a sort of constant, and it might be much better to put variations in the rig.
Yeah.
I've never seen such stupid rigs designed as on these reconstructions
Yeah.
of ships. Masts should be far lower.
Yeah. Yeah. But that digital model is exactly as the Bremen cog replica. So we were testing the replica that they used there.
Yeah.
I agree, and it's in my report. This is the minimum of a mast and sail that can function. I don't like it. It's what they're using on the
The
replica.
last man who really knew about rigs was Herman Pedersen. And we should find another man like him to say what probably has been the rig, and it would have been extremely different from what is used now on these replicas.
Yeah. And we were actually doing a little bit of that last year with the replica of the Carina vessel. We were testing some of the wind angles and changing the rake of the mast and the yard, but then the ship sank. We had a leak. So it's unfinished work.
Goed in de microfoon praten.
Hello, I'm Betty. I'm working at Glavimans shipyard down in Laat. And even when you see with the normal 2D drawings, you could see differences in the construction because it's always flat.
Yeah.
The 3D making drawings is just 10 years. So for the moment, what you see now is that everything should be complete. You can use the 3D model also for fan calculations or whatever. But even in real time, now on shipbuilding, you will see differences with connections between the difference of drawings, because not every drawing is always updated. So that I'm surprised, even when the vessel is always already 100 years on ship bottom of sea bottom. You can see differences.
But even the professional ship draftsmen that worked for Ferry Yacht Design back in the 1950s, they were proud if they could get two drawings to match within 1/8 of an inch, 3 millimeters, if their paper drawings could be that good. Us as archaeologists and amateur draftsmen, there's no way we're getting that 3 millimeter accuracy in two paper drawings. But if the model is made as a 3D digital model and the computer makes the two slices for the drawings, 100% guaranteed these two drawings match all the time. Because there's no human moving from page to page to make the two drawings.
I'm working already 25 years in shipbuilding, but I start also on the drawing board, making drawings, and now I'm in 3D. You can see that there's a lot difference between building a ship and preparing it within 3D, but I'm very pleased to see this. Thank you.
You told us the ships that float. How sure are you that your digital model will float?
Based on the boat that I built, which I actually sailed on, and we leave it sitting in the water every day. We then built an exact digital model of the same ship and asked the computer to make it float.
Yes.
And it floats exactly the same once we match up all the objects that are in the digital boat to to the physical boat. So I started with just the timber, and it floated too high. I said, oh, well, we left in the anchor and the ropes and the life raft. I added those to the digital model, and the two came almost, not 100%, but 99.8%. 20 kilos of a difference.
So you're sure?
Yeah. If the computer says it will float, I'm happy to go sailing on it.
Hi, I was wondering, have you come across in your research or your experience that sometimes it's not a bad reconstruction, but it might be a bad ship?
Oh yeah, absolutely. There's thousands of shipwrecks out there. There is a report, the Washington report, that was done in the 1800s, where they went around and documented ships that were still in the harbour. That's a bloody stupid idea, because the ships that were out there fishing and doing work and catching fish. They have a drawing, it's a Kinsale hooker. It's supposed to have been a really famous Irish sailing ship, which eventually died out when the English fishing fleets came in. And they have this drawing published in the report. It is the most stupid looking design I've ever seen. It's horrible. But this ship is famous all over the south of England, all down into the France, Spain, Portugal. These were a fantastic fishing boat from Ireland. Somebody built a bad one and left it at home in the harbour. Yeah, mistakes happen. Even as boat builders, we make mistakes. So yeah, there are bad designs, definitely.
Thank you. Leenstra has been a lot with the Glavia, and so asking the kind of questions which maybe Willem Vos would have posed himself. How did you deal with the specific weight of the wood?
Yeah, so the majority of the time we're using average wood densities. It tends to balance itself out, because even when I was 15, 20 years ago building ships, okay, we all want lovely heartwood, grown oak frames. We don't always find them. There's always some sapwood, there's even some bark left in the timber. So by the time you work through 40, 50 pieces of timber, even with averaging it out like I did with that smaller boat, the difference in the weight, everything else, like I put all the iron exactly, because iron is standard density. So the only variable there was the weight. With 1,800 kilos of total timber weight, we were only wrong by 20 kilos in 700 pieces of timber in that small little boat. So yes, there is a little variation there. If we know exactly, we can tell, like I have the different densities for the different types of timber, even the difference between oak that's completely waterlogged, 27% moisture just sitting out there like the replica outside, or freeze-dried and treated peg conserved timber. So we know the differences in the shrinkage and the weight, but then the difference where like you can carve two blocks of timber there and they'll be slightly different with where the heartwood, sapwood and everything is. So there is slight variation, but it's not enough to really change. Like on a boat the size of Bremen Cog there, to change the displacement by 1 centimetre of depth, you're going to need close to 600 or 800 kilograms. So losing 30 or 40 with the average density of the timber won't really modify it too much.
Yeah, because the Will would have said the boat will be in the water a lot more stable than it will be on the side. Because the lower wood will take a lot of water in it, and so the center of gravity will be a lot lower.
Yeah,
I wonder whether you can, because I tried to have sarpias and trying to make a specific weight dependable from the depth in the hold of the ship. And it indeed made a lot of difference in the center of gravity, so in the number of ballast it would need.
Yeah.
We know.
It would change a little bit.
Of the Batavia, which indeed has a lot of problems.
Yeah, so like the difference between fully waterlogged oak and 27% up at the surface. 27%, it's 800 kilos per cubic meter, and fully waterlogged is going to be 1.12 kilos. It's about 200 kilos per cubic meter of the difference. So we can model that up pretty accurately. if you want to say these 4 are fully waterlogged and these are only air dry, we can model the difference between them, yeah.
You doing that also?
Yeah, it depends on the ship, but it's very rare to find timber that's 100% waterlogged. It becomes kind of a wet sponge, pile of stinking rot.
You used 3D scanner for the modeling of the ship. Would photogrammetry be a viable solution for these things?
Yes, it is, but photogrammetry, there's a few people here who've heard me shout and scream this all day yesterday. Photogrammetry takes a bunch of photographs, matches them together, and makes a 3D model. It's never the right size. You have to always apply a correction for the scale of the size. It's fine if the computer gets the matching right in every one of the pictures and doesn't make a mistake and start going this way. You don't see that until you've gone home and processed all of the photographs into the digital model. Laser scanning shoots a beam, takes it back, knows an exact measurement, 100%, within 1 or 2 millimeters, guaranteed. Measurement to measurement to measurement. What I'm doing now is using laser scanning to take the exact shape and size and using the photographs to put the lovely high resolution texture onto the physical scale model that's correct from the laser scanning. If I'm above water, laser scanning all day long. Go rent a machine, it's only 200 quid and do the laser scanning. It's quicker, faster result. Take the photographs and use that for the texture. But if you're underwater, photogrammetry is still the best solution.